All right, welcome to the final talk in the hottest event for junior researchers in 2022. We're very happy to have Philipp Joram tell us about final coalgebras of analytic functors in HoTT.
Thank you, Emily. Yes, so I'm going to do some category theory in homotopy type theory, or rather attempt to translate some category theory into homotopy type theory. And this is, well, joint work with my supervisor, Nicola. And yeah, so what are we going to do? Essentially, I kind of want to revisit what category theorists know as Adamec's theorem. And Adamec's theorem gives us sufficient conditions for an endofunctor to admit a final coalgebra. Or maybe you're more familiar with the statement the other way around, where like an endofunctor admits a initial algebra. And the question here is that, at least I'm interested in, is which functors satisfy these conditions in homotopy type theory, and can we even apply this theorem? And I want to kind of focus on analytic functors, which are a particular class of functors. And for this talk, let's just focus on multiset functors, because that's a nice case study, and it sort of like already shows kind of what should be going on, like a general case. If you've never heard of any of this stuff before, there's some like neat applications. So the first of them is you can use this sort of theory to give categorical semantics to co-inductive types. So in that case, your endofunctor describes some sort of signature of your co-inductive type, sort of like how many constructors are there, like what are the arguments. And the final coalgebra gives some sort of like co-recursion principle. And if that is not the like thing you're interested in, there's another thing where people doing dynamical systems or discrete dynamical systems use this to describe their transition systems or automata. So in that case, your endofunctor gives you some sort of space of reachable states. And if you have a coalgebra of that endofunctor, that's some sort of transition function. And the terminal coalgebra then describes bisimulation between automata or systems of this sort of shape. Before we start, I'd usually say, well, please ask questions, but I'd say, let's just postpone this. If urgent, notify the moderators. Okay, and let's start with some background that we're going to translate. So first, the obvious thing. Let's talk about some arbitrary endofunctor in your favorite category. Then F coalgebras over that thing will consist of an object in your category and a morphism from that object into the application of your functor. And then you can ask the natural questions like, what is a morphism between such F coalgebras? And that is in general just sort of like the obvious commutative square, where you plop in F at the top and the application of the functor to your F at the bottom. And then you can ask, well, I mean, this forms a category. Is there any interesting objects in that category? And well, one of them is the question sort of like, well, is there a final or a terminal object? And we call a coalgebra final if the coalgebra, well, there's exactly one coalgebra morphism into it for any other coalgebra. And a bit more complicated stuff as a warm-up for the next thing. For these sort of endofunctors, we can define so-called final omega op chains, where omega is just the first ordinal. And these look at like some sort of application where you have in the left of your diagram the unit object, like the terminal object of a category. And then you have into it the unique map from F applied to that object. And then you just iterate this, well, omega many steps. And if you're lucky, sometimes this has a limit. And the limit of this sort of diagram exists, and we call it LF. And it comes with these little legs you see. And for technical reasons, we also sometimes consider the shifted limit, or well, the limit of the shifted chain that just starts at one step later. And what is this used for? Well, this is a classical and also historical result by Viera Polava and Jirji Adamek that says if your functor admits such a limit, like the limit exists, and the functor also preserves that limit, then there exists a coalgebra that sort of like has as a carrier the limit, and that coalgebra is final. And that's pretty neat because there's a wide variety of functors where this just applies. And in particular, polynomial functors and classically analytic functors that I'll introduce in a second. So what's the idea of the proof here, which is kind of what we want to see whether that works in HoTT? Well, the statement that your functor preserves the limit is essentially just giving by a particular isomorphism. And by some abstract nonsense reasoning, we can say that the limit is the same as the shifted limit. And then we construct a coalgebra, I call it fix, that goes from the limit into the application of the functor into the limit by just composing the two isos or their inverses. So as I said, we're going to do this for analytic functors. And these are sort of generalizations of polynomial functors. When you think of your polynomial functor, it's sort of like a sum of products of things. And they were introduced by Worrell in the 80s to do enumerative combinatorics. And I'm going to use a definition of Hasegawa here, which is sort of like a normal form for these sort of things, where we call a set endofunctor analytic if it is of the form where like f of x is a sum over some set A, and the individual summons are products by some finite set BA modulo some subgroup of automorphisms, where you look at automorphisms of this finite set. So think a subgroup of permutations. And we say, well, what's the quotient here? Like if you compare two elements V and W, you say that they're related if there is a permutation in your chosen subgroup that permutes the indices in this product. And that's nice. If, for example, if your group here is just always the trivial group, then, well, nothing happens and you recover polynomial functors. And we'll see what happens at the other extreme. So this has a nice encoding in homotopy type theory because like you do the naive thing and you just write all of this down for functors that are sort of, well, type constructors or maps in the type universe. And so these come with an extra action on maps that I kind of suppressed here. And the nice thing is that the limit as a type always exists. And we can always write down the preservation map, just kind of completely arbitrary, like it doesn't matter what f is. And there's no restrictions on the age levels of the types involved yet. We might impose some later, but just for writing it down, there's none. And then our questions become, is this function, this preservation of limit function, an isomorphism also constructively, or let's say in our setting of HoTT? And is this fixed point in Adamec's theorem still like a final coalgebra? Okay, let's start our first attempt by looking at finite multiset functors in H sets or in, well, homotopy types that are sets. And to get on the same level, what is a multiset? Well, sort of like laxly speaking, a multiset is a collection of stuff of some sort X. And this collection of stuff keeps track of multiplicity of elements, but it doesn't care about order of things. So I don't know, if you look, for example, at the multiset containing pastry and coffee, that's the same as coffee and pastry. You can reorder the elements, that doesn't matter. But it's not the same as, well, having coffee twice. If you're, well, you will notice if you like coffee, that's not the same, but yes. And how can we encode such a thing? We can see that, for example, one model of finite multisets would be free commutative monoids over some chosen type of elements X. So we can define a higher inductive type of this free commutative monoid such that there's an empty multiset, which is some sort of null array constructor. There's singleton multisets, and then we can take binary unions of these. And since we always only have like finitely many applications of constructors, this will give us sort of like finite unions of things. And then we just stipulate that we have additional path constructors where we say that the empty set is neutral with respect to the union and that the union is commutative. And also, we will have to truncate this to be a set because otherwise things go wrong. And also, we're talking about multi-sets, so I guess that makes sense. But of course, there's different presentations of this sort of stuff. So for example, another way of doing it would be you take lists over X, and then you set quotient then by permutations, and you choose your favorite like implementation of permutations. Or you define another high inductive type that looks like lists, so it has a nil and it has a cons, but also there's one extra path that permutes the head of lists. And then there's also another way of doing that, which is kind of closer to what we saw earlier. We can define this as some sort of analytic functor. So we can define finite multisets over X as some natural number k, and then vectors of k elements in X modulo some relation. And that relation is the existence of a permutation of a k element set, such that this commutes with the elements of our multiset. If you ask whether it is relevant here, like whether this is a truncated existential or not, it doesn't matter. You can do both. It's equivalent. But this is a nice definition that sort of just fits the pattern of analytic functors. So like my pattern matching brain likes that. And yes, as a note here, all of these presentations are naturally equivalent. So they're not just like equivalent as types, but also they commute with the correct maps. And we can prove theorems with these presentations as we like, because some of them are more convenient in some situations, some of them are well, some of them you better not use in some situations. And well, since we have univalues, we can just transport between them. That's kind of nice. So let's try and apply Adamec's theorem in one of these cases and see that will fail, which is, well, if you're a fan of no-go theorems, this is for you. If not, this is a bit sad. But it is sad for interesting reasons. So we can say that the preservation function for this preservation map for the free commutative monoid is surjective. We can prove this. But the injectivity of the thing is equivalent to a classical principle, which is called the lesser limited principle of omniscience. And this principle states that if you have a stream of Boolean numbers, if you have a stream of Booleans, and you know that the stream is true at most once, then merely either all of the odd positions of the stream are false or all of the even positions of the stream are false. And important here is that you don't know where it is one. You just know sort of like, well, it's, well, you don't know where it is true. You just know that it does that at most once. And you can't prove that sort of like purely constructively. And how does the sort of like proof here work? Like just as an idea, the idea is that if you assume the injectivity of this function, then from the injectivity, you can merely extract paths of two-element multisets, and you can use these cleverly defined paths to then decide the above problem. So this proof actually goes through already for sort of like unordered, well, let's say at most two-element sets and not just multi-sets. But it's kind of interesting to see that you can sort of like engineer this sort of property. Let's try and fix that. Let's look at finite multiset functors in groupoids. So we saw before that kind of like what went wrong here, or like, let me tell you what kind of went wrong here, is that the permutations involved in all of these definitions at some point, they are proof relevant. So they're important. And in this proof of preservation of limits, you will have to have access to these permutations at some point. But since they're set truncated, you don't really do that. So you're kind of like needlessly forgetting about the permutations. And if you want to prove anything about them, then you sort of like need to reconstruct them out of thin air, and it doesn't work. Or at least the way that we approach it doesn't work. So instead, what we came up with is we define something that lives in groupoids, or something that is in H groupoid, and that keeps the permutations around its data. And we show that this thing preserves the correct limits and also admits a final coalgebra. And then we relate it back to our more intuitive definitions of finite multisets. So here is a suspiciously simple definition. We define the type of bags, dependent on some type X, as a big sigma where we index by some finite set, and then with this comes a function indexed by that set. So we call the first projection of this thing the cardinality, and the second projection just the elements of this bag, type of bag. And we encode sort of like being a finite set as the usual bishop finite, and we call the angle bracket thing the underlying type. And the intuition here should be that this thing has the correct path type. So sort of like the homotopy type theory 101, where like you kind of have to look at the path type first to do anything else. So if you pick any two bags, X's and Y's, and you want to know when they are the same, well, this is equivalent to saying that you have, as in constructively, that's a sigma, not something truncated. You have a permutation of the carriers or the cardinalities that commutes with the elements. And the interesting part here is, I guess, that these permutations or these equivalences, there's potentially a lot of them. So if, for example, your cardinalities are Booleans on both sides, let's say that, then you already have the identity and the swap. So there's, of course, multiple ways of relating these sort of multisets. And also, just as a sanity check, well, this thing kind of like nicely respects H levels. So if you put a groupoid in, you get a groupoid out. The question, of course, this is sort of like, actually generalize the thing that we had before, and I would say, yes, it does. So if you set truncate this construction, then you get back the original finite multisets in whatever presentation you prefer. And the proof of this is sort of like standard use of like all of the eliminators you have at hand, except for one case where you actually need to define a weakly constant function to go out of a proposition in a set. And I just think that's neat. So I wanted to tell you that. So you can't do the sort of purely stubborn approach. You have to be a bit creative at least. And now for the nice part of this definition is that we can say that this functor preserves the correct notion of limits. And we do that by just, well, invoking other people's work. And there's this nice paper by Benedict Ahrens, Capriotti and Capriotti that says if you have any type A and any type family B over that, and you look at the sort of in like homotopy type theory version of polynomial functor, then this thing preserves the correct, like these omega op chains, or the limits, I'd rather say, and admits a final coalgebra. And so our theorem kind of becomes a proof by definition, where the hard part is not so much coming up with like this data type and then proving something insanely hard, but coming up with the right presentation of the type. And we can just see that our bag that we have is a particular instance of such a polynomial functor. But you note here that in this thing, this is a construction that goes from, oh, I should probably say that, from types to type. So it's completely unrestricted in H level. But you can just instantiate it. So the hard work was just like banging something that looks like a multiset into the shape of something that looks like a polynomial functor. Yeah, and that's how we get our like nice final coalgebra. Question: can we recover a final coalgebra for the like set case from this groupoid case? And well, the answer here, I guess, is maybe. So we saw that in the first part of the talk that the application of Adamec's theorem in the sort of like set case failed. But that doesn't mean that it's in general impossible. It just means that I'm not clever enough to prove it like with this tech. Well, it doesn't work with this technique, and I'm not clever enough to do it with another technique. So the working hypothesis here is sort of that maybe the final coalgebra that we got in Groupoids descends through the set truncation to something for like finite multisets. And like a first reassuring result, which kind of looks like the conclusion of Lambeck's lemma, if you're familiar with that, is that this truncation is actually a fixed point of finite multisets. And do we have the time to do that? Maybe. Well, I'll skip it for now, but the proof is sort of like a nice, just equational reasoning essentially along like all of the things you prove along the way. But the thing that's like not so nice, I would say, is that to prove sort of actual finality of this coalgebra, we need some version of choice. And the way I've done it so far is like we need to assume two different versions of the axiom of choice from, like you can find it in the HoTT book. They're just like sort of exist at different truncation levels. But if you assume those, you get an actual final coalgebra for finite multisets. And my conjecture is that this is actually necessary. I don't know whether it is for sure, but it seems like, because if you look at the proof that we have for now, is you need to derive an equivalence of certain function spaces where you permute a set truncation out of it, but there's also like a groupoid in there. So it's like not entirely clear how that should work in general. Of course, for a particular x, you can always do that, but you kind of need to do that for very much arbitrary x in the proof. So with that, and like 5 minutes of time left, let me just conclude here what this sort of like case study was about, I guess. We have looked at a bunch of multiset-like functors and sort of like just an exercise to get warmed up with homotopy type theory for me, I guess. And we have looked at analytic functors in sets, and they seem to be ill-behaved constructively in a certain sense. And at least we can't really get sort of like an Adam-X theorem without more classical principles, because this pathology I noted earlier will kind of always occur if the functor is like not directly polynomial. But we can sort of like go one step up in the H level and one step down in the complexity of the definition. And we can consider polynomial functors in groupoids. And those admit a final coalgebra. And they also capture the right notion of symmetry. And yeah, I guess that is it from my side. And I thank you very much for your attention, for bearing with me. There is some cubical ACDA code that proves many of these claims. Feel free to have a look. And yes, thank you very much.
Wonderful. Thanks again. Let's do our visual silent applause. All right. Are there any questions for Philipp that you'd like to include on the recording? All right, maybe rather than put anyone on the spot, I will stop the recording. Thank Philipp again, and then we'll continue our discussion offline.